So we are looking in your textbook on page 51, and I believe page 27 of your unit handout for the multiple choice numerical response questions. Just to go through a quick review here, and there is an awful lot of information in terms of the inverse of a function or the inverse of a relation. By the way, I've kind of interchanged that. I've sometimes said inverse of a relation, sometimes inverse of a function. It doesn't really matter, because in this course, anything we take the inverse of will start off as a function. And I didn't mention this yesterday, but a relation is a broad set of things that include functions. Not all relations are functions, but some are functions. Okay, so the inverse of a function, inverse of a relation, I'm not really picky about the difference between the two. The inverse of a function is found by interchanging the x and y coordinates of each point. What that ends up doing is reflecting the graph of the function across the line y equals x. The mapping is that x comma y on the original function becomes y comma x on the inverse. And again, I feel the need to say that when we talk about this part of the mapping, this statement here, I'm not meaning to suggest that on the inverse the first number is a y coordinate. The first number in that ordered pair is an x coordinate. It's just the y coordinate that was on the original becomes the x coordinate on the inverse. Every property of x and y switch. So yesterday, I don't know if this was no, this wasn't the example we looked at. But yesterday we went through the process of graphing an inverse of a function by swapping x and y and drawing all of the points. And then we were asked for the domain and range. We were asked for the domain and range of the inverse, and I made a point that you didn't have to graph the inverse to determine the domain and range, because if you look solely, just imagine that you can't see this, you look solely at the function. The function has a domain that goes from -6 for x up to +2 for x, and it has a range, this is the original, with a minimum y value of 4 and a maximum y value of 7. Does that look legit to you? Those numbers? Looks okay? I'm asking because I don't have my glasses on, and sometimes when I'm looking at things up close, I can't read them very clearly. But it's fine, yeah? Okay. So if I said to you, what is the domain of the inverse, since you switch x and y in the equation and on the graph, really what it boils down to is everything that was true about x in the original, namely that x had a domain from and including -6 up to and including x equals 2, will become true about y in the inverse, which means that the minimum y value will be -6 on the inverse, and the maximum y value on the inverse will be +2, because those were the numbers that fit with x. And you could do the same thing and say that the domain, you could do the same thing for domain and say the domain must be the set of numbers that were the set of numbers for the range, because x and y switched, and that would be 4 to 7. And if you come back to reality and actually take a look at this graph and determine the domain and range of the inverse by looking at the graph, you'll see that it matches that logic. To determine the equation of an inverse, you swap x and y in the equation and rearrange for y. Now, the inverse of a function may not be a function. I've got an example here of an original function in blue, which is not a parabola. And remember, we had this discussion yesterday that a parabola has a left and a right side, so the inverse will have a top and a bottom. Well, I've got an absolute value function as the original function, and an absolute value function has a left and a right side. So that means the inverse is going to have a top and a bottom. And the inverse of this function in the diagram shown is not a function, because it will fail the vertical line test. And more specifically, on the pink graph, there are values of x that produce multiple values of y. Okay? That's why the vertical line test is used. So quadratic functions, absolute value functions, any function that goes up and down in any way, anywhere, will not be a function when you inverse it. The inverse will not be a function. Because if the original goes up and down, the inverse will go left and right. If you want to restrict the domain, then you have to change the values of x that are allowed for the original function so that when you reflect it across that line, you get not a top and a bottom. You get only a top or only a bottom, because then it will pass the vertical line test. And what I'm saying here is, if it's a parabola or an absolute value function, h, the horizontal parameter h, is the key to the solution to this, because you can always say x is less than or equal to h, or x is greater than or equal to h. So if I take this original function, this is the same function I have here, x plus 3 quantity squared minus 7, I've put here, but I've said let's only use x is less than or equal to negative 3. And if I use only x is less than or equal to negative 3, then the original graph only has a left side, which means the inverse only has a bottom. Left being a negative thing, bottom being a negative thing. And the same thing goes with only looking at x is greater than or equal to negative 3. Now, one final thing, when you look at the equation of the inverse of this function up here, and not worry about restricting the domain, the inverse has that plus or minus. I think it's useful, but I don't think it's absolutely required. But I think it's useful for you to remember that the half of that equation that's positive root will be the top. So if you look at the right-hand side of the screen here, y equals positive root x plus 7 minus 3 gives you the top half of that red graph. And y equals negative root x plus 7 minus 3 gives you the bottom half. So all that being said, does anybody have any questions? Go ahead, Arden. 4b? Certainly. So we want to restrict the domain for which the function has an inverse that's also a function. And again, this is one of a number of things that I've always struggled with as a teacher, because to me it seems easy, the explanation makes sense, but students struggle with it. And what I would say to you is always try to go back to the idea that the inverse of a function will not be a function because the function, the original thing, goes up and down. So if you can change this blue graph in 4b in some way so that it only goes down or only goes up, then the inverse, don't worry about what the inverse will do, but the inverse will be a function. So what we can do is we can either focus our attention here on try that again, that side of the parabola. So if I could ignore the side I didn't highlight, then the inverse of what I did highlight would be a function. Or I could ignore the left side and only focus on the right side. And if I could only focus on the yellow side, the inverse would be a function. I think students can get bogged down in what it would look like. I don't care what it would look like. That's not relevant. So the value of x that kind of separates those two halves is negative 2. And that means if we say, for the pink one, if we say x is less than or equal to negative 2, if we say x is less than or equal to negative 2, then we are going to get the pink graph. But if we say x is greater than or equal to -2, we are going to get the yellow graph. And that's it. So again, in terms of a translation, a parabola, before it's translated with any h and k, has its vertex at the origin. If the vertex is over at -2 for x, regardless, everybody, of where this thing is vertically, if the vertex of this parabola has an x coordinate of -2, then h is -2. And this goes back to my statement here that for a parabola or for an absolute value function, that's going to be the case. Is that good? Other questions? Go ahead.
For question 15 in the textbook, just A, don't know how to show the inverse when it actually does.
Okay. Yeah, I get you. So if I gave everybody these functions, g of x equals 3x and h of x equals 1 over x and p of x equals x squared minus x. I just, you have a catalog of functions, and I'll get to your question in a second. And I say to you, if that's the case, determine h of 4. Whoops. If I say determine h of 4, then what that means is h is telling you which function to use, and 4 is saying the x coordinate is 4. So all this is saying is go to the h function, which is 1 over x, and change the x to 4. That makes sense? Okay. So if I now say to you in A, what is this? Then we need to know what this function is. Because f to the -1 of 4, which is the inverse function at 4, f to the -1 of 4 is just saying take f to the -1 of x and change x to 4. So what we have to do is take this, which is y equals 4x minus 2, swap x and y to get x equals 4y minus 2, and rearrange for y, and whatever we get is the inverse of the function, which is f to the -1 of x. Okay. So if I rearrange for y, I'm going to have y equals 1/4 x plus 1/2. So I've divided each term by 4. And now it's a matter of saying if f to the -1 of x is 1/4 x plus 1/2, f to the -1 of 4 is 1/4 times 4 plus 1/2, and then you work out what that is.
So when it does have the function, the inverse function, what follows is already been inversed.
Yes, that's what the word equals means. F to the -1 of x is the inverse function. And if I say it equals to something, it equals to the inverse function, which somebody has already inversed it. Yes. Yeah. I mean, you could, if you wanted to be really sly about this, you could say, and this is the legit strategy we're going to use when we talk about logarithms and exponential functions, that if you want to find this, then what this is saying is that's what this is saying without using notation. It's saying when x is 4, what's the y coordinate of the inverse? That's what it's saying. So you could be sly about it and say, well, what I'm going to do then is this. I'm going to say that since to find the inverse involves switching x and y, why don't I just put 4 in for y in the original and solve for x? And that will work as well. Other questions? Okay, we're going to move on today and start chapter 2. So there are no other questions. I'm assuming that you can do all of the multiple choice numerical response questions. Let's take a look on page 29 of your unit handout at radical functions and transformations, which is, as I said, the start of chapter 2, which is the other part of this unit. I think we have 3 lessons here we're going to cover. And again, that'll put review days next week at Wednesday and Thursday, which means your unit exam next week is Friday. We're going to be looking at the graph today of f of x equals root x. And then, really, everybody, everything we have learned about transformations, we're going to apply to this graph. That's all. So we're going to be applying a, b, h, and k to the square root of x equals a function. So there are some base functions. Could you put your mask up? Thank you. There are what I call base functions. And as we get through this course, you'll see more and more of them. What I mean by a base function is something like y equals x squared. Everybody should know what y equals x squared looks like. It's a parabola whose vertex is at the origin. If the tip of my nose is the origin, the parabola looks like this. It starts here and opens up. To the left and to the right, it moves up. We know what that looks like. And by knowing what that looks like, you now have opened up a whole host of pieces of information or skills in terms of variations of that graph. Meaning, if you know what y equals x squared looks like, you should be able to graph that by looking at a, b, h, and k. Because that's just an application of y equals a times f of b bracket x minus h plus k. By the way, a is negative a third, k is 4, b is 2, and h is 2 as well. Because you would have to factor out this 2 out of the 2x minus 4 to be left with x minus 2, revealing that the true value of h is actually 2. Okay? Just a side note. The broader point I'm making is by knowing what y equals x squared looks like opens the door to knowing what a lot of quadratic functions look like. And throughout the course, we're going to be looking at other functions. You're going to learn what y equals x cubed looks like so you can apply that. You're going to be learning what y equals x to the n looks like, so x cubed, x to the 4, x to the 5, x to the 6. We'll do that in the next unit. 2 to the x is an exponential function that we will learn about. Absolute value of x is already a graph whose visual you should have in your head. It has a vertex at the origin, it opens up, but it consists of 2 straight lines, making a V. The slope of the right-hand line is 1, the slope of the left-hand line is negative 1. And there are all these functions. One of them is root x. So it's an expectation in this course that as we go through all of these functions, including sine of x and cos of x and log base 2 of x and 1 over x, that you can apply this template that's on the right to that function. And again, what we're doing today, I think I've made my point, but what we're doing today is we are focusing our attention on that function. Okay? So to begin with, what is a radical function? A radical function is any function where the independent variable x is included as part of a radicand of a radical expression. What does that mean? Well, here are some examples of radical expressions. What is a radicand? A radicand is the thing underneath the square root. And I'm going to have to now take a moment. I want to explain this now to get it out of the way so I don't have to keep explaining it again and again and again. So we're just going to take a real detour away from this because there's a terminology that's important in math that you probably are not familiar with. If I give you 2x squared, this is squaring something, right? The operation here is squaring. If I give you the square root of x plus 1 the operation is square rooting. If square rooting is an actual verb. I don't know if it is, but that's what you're doing. If I give you tangent of 3r, then these are all operations. Then the operation is this, right? And I'm pretty sure that's not an actual word, but that's what you're doing. You're doing a tangenting to something. If I give you log of 3y, the operation is logging. That is a word, but it's not a mathematical word. It means to take the logarithm of something. Are you with me so far? That these are 4 examples of operations. There is something in mathematics called the argument. Is that how you spell argument, or is there another E in there between the U and the M? Who cares? I'm with you on that. There is something in mathematics called the argument, and the argument of the first operation is 2x, the argument is x plus 1, the argument is 3r, and the argument is 3y. In other words, everybody, the argument of a mathematical operation is what you're operating on. Okay? To me, it's always seemed as though the argument should be what's happening. So the argument should be squaring, square rooting, tanning, and logging, but it isn't. The argument of a mathematical operation is what you're operating on. Okay? So I go through that because I'm going to use that word a lot in this course. In other words, x has to be part of the argument of a square root. Okay? These 3 things I've highlighted are the arguments of those radicals. Well, the most basic radical function, the one that would contain x as part of the radicand and be as simple as possible, I hope you would agree, would be y equals root x. I don't know how much simpler you can get and still have x as part of the radical. I want to make a note here, everybody, that this symbol written on its own means what we call the principal square root. And it means the positive square root. Because sooner or later, one of you are going to say, well, shouldn't we have plus or minus there? And I've done a good job, I think, of kind of conditioning you to this. I've always said you put plus or minus when you introduce the square root. The square root's there, it is what it is. So this is only the positive square root. We're going to look at this graph here, and I've got a table of values set up for you. You have that chart as well? Okay. So I'm going to choose, well, just stop for a second. Is it clear why I've chosen these numbers for x coordinates to put into the function? It's because they're perfect squares, and I'm going to put x equals 1 into this function and x equals 4. And I'm going to get numbers that I can identify with quite easily. So the square root of 1 is 1. Well, identify with is the wrong word. I can calculate as a whole value without decimals. It's going to be a rational result. The square root of 4 is 2. The square root of 9 is 3. The principal square root of 16 is 4. The square root or principal square root of 25 is 5. And we can plot these points. And the purpose of this little exercise is simply so that you can get a visual of what y equals root x looks like. And it's probably not going to be a surprise to you. It goes through the origin, and when x is 1, y is 1. When x is 4, y is 2. When x is 9, y is 3. Square root of 16 is 4. Square root of 25 is 5. I don't know why I've skipped one there. I lost the slide. That's okay. Square root of 25 is 5. And if you were to connect them with a smooth curve, you're going to get half of a parabola that's laying on its side, which makes sense because square rooting is the inverse operation to squaring. In other words, if you took y equals x squared and you found the inverse, you would get y equals plus or minus root x. The plus root x is the top part, the minus root x is the bottom part. But since this has the principal square root, that's what it looks like. So let me pause here for a second. Not only would I say that you need to know That's the general shape. You need to know specifics of it. So just like I hope you know that y equals x squared goes through the origin, and when you go over 1 on both sides, you go up 1. And when you go over 2 on both sides, you go up 4. And when you go over 3 on both sides, you go up 9. Just like you know that pattern, I'm asking you to get this pattern in your head. You're not going over, you're going up because it's an inverse. You go up 1, you go over 1. You go up 2, you go over 4. You go up 3, you go over 9. And I would say that all of these points are, well, I won't draw arrows to all of them, but I will draw to a couple. These are what we call key points. They are points that help you get a better picture of the graph of the function. And all of the red points are key points. Okay. So this is maybe a bit of a lie. I say all radical functions can be graphed by transforming that function. It's a lot or most. I can probably come up with some radical functions which are not transformations of that. The square root of the sine of x is not going to be a transformation of that, right? If you apply the template, here's the template that we've been learning about gradually from the beginning, and we concluded our exploration or learning about this yesterday when we said we could combine everything, or the day before when we said we could combine everything. If you apply that template to f of x equals root x, you get y equals a root of b times x minus h end root plus k. I want to explain why you get that. This, let me write out the function. F of x equals root x. So if I start talking about y equals a f of b bracket x minus h, then plus k, this means the square root of b times x minus h. Why does that mean the square root of b times x minus h? Because in this question, or on this page, f of means take the square root of, because that's what f of x is. So all I'm doing is, it's just like if I said if f of x is root x, what's f of 3? You would say it's root 3. What's f of b times x minus h? The square root of b times x minus h. And then, of course, you have to multiply that by a and add the k. The reason why I think you should understand how you can build that is it's not on your formula sheet, which I will. You'll get a formula sheet eventually. I still haven't given it to you. Is that correct? Okay. This is not on your formula sheet, this y equals a root b bracket x minus h plus k. So if you understand how to produce it, you will understand how a, b, h, and k fit into root x, which will be helpful. Okay, so example 1 says sketch the graph of each radical function using transformations of the most basic radical function. Also state the domain and range. So it shouldn't come as a big shock to you that in order to do this, you need to look at the graph. Sorry, you need to look at the equation, and from the equation, identify a, b, h, and k. So that's what I would like you to do to begin with here. Keeping in mind that you should rearrange this for y to get 3 root negative 1 times x minus 5, and then you're going to have minus 1 at the end. So I would like everybody to write in what you believe a, b, h, and k are equal to. I have a equals 3, b equals -1, a equals 5, and k equals -1. Are we in agreement there? Okay, no problem. So I'm just going to erase what I wrote in brown here. I think, quite frankly, you should be able to look at what the equation of the function is and see that k is -1. Like, move that over in your head. So what's going on here? We have a vertical stretch by a factor of 3. That's something that's happening because a is 3. We have a horizontal reflection because b is -1. Because b is negative. The fact that b is -1 tells us although there's a horizontal reflection, there's no horizontal stretch. The stretch factor is 1. And then since h is 5, we are going to shift this 5 units to the right, and k is -1. We're going to shift this 1 unit down. Now, I'm going to start to cheat a bit here, and we're going to be doing this in a number of places in this course when it comes to a, b, h, and k. A and b have to occur first, right? That's the rule. But what's interesting or maybe important about this particular function is regardless of what a and b are, this point, which I can call the vertex, is not affected by a and b, because it has an x-coordinate of 0 and a y-coordinate of 0. Any horizontal or vertical stretch or reflection won't change it. And that means, regardless of what happens to this graph, it's going to end up shifting this point 5 to the right and 1 down. The vertex of this point has to be here. The vertex of the graph has to be there at the end of everything. Yep.
What about the horizontal reflection?
We'll get to that. It doesn't matter. The horizontal reflection will flip the graph over, meaning it will not, generally speaking, Ian, it will not do this. Instead, it's going to do this. But it's not going to change where the vertex is. And by the way, this is not how we're going to draw the graph. I'm just jumping to the end conclusion that the vertex will be at h comma k, just like it would be for a parabola. Remember last year we said the vertex of a parabola is always at p comma q? Well, p is h, q is k. The vertex is at h comma k. The vertex here will be at h comma k. So that's just a point I want to make to begin with. Let's go with the original function, though, and I'm going to take all of these points and apply transformations to them. I take this point right here, this one that's wiggling around, and I stretch it vertically by a factor of 3. Done. Hasn't moved. I reflect it horizontally. Done. I now shift it 5 to the right and 1 down, further illustrating my point that a and b don't affect the vertex. Well, let's take another key point. Another key point is at 1 comma 1, because when x is 1, the square root of 1 is 1. I am going to stretch that vertically by a factor of 3, which means it will be 3 times further away. Not 3 squares further away, 3 times further away. So it was 1 away, now it's 3 away. I'm going to reflect it horizontally across the y-axis, and then I'm going to shift it 5 to the right and 1 down. 1, 2, 3, 4, 5, and 1 down. And Ian, you had asked about what about the horizontal reflection. We can see now if I start to connect these 2 points, it has to curve up and to your left. And we have another key point. You know, I would say you could probably draw this now with just those 2 points. Let me get rid of that. With just those 2 red points. But I think putting one more, using a 3rd point, really adds some more texture to your diagram. In other words, it becomes more complete. So that gets stretched vertically by a factor of 3, which will mean the y-coordinate will go from y equals 3 to y equals 9. It reflects across the y-axis because it's reflected horizontally, and then it moves. I'm just going slow here because I'm counting squares to make sure I get the right distance. And then it moves 1, 2, 3, 4, 5 to the right and 1 down. So generally speaking, and I'm not good with drawing curves on the smartboard. But the point is, I think if I ever wanted to test whether you could graph transformations, I would not use this function. I would use something with straight lines. Anyway, it's going to look kind of like that. That's not bad. Got a little wobbly at the end there. That's what the function looks like. So what is the domain and range? Well, we can see that the domain here is x is less than or equal to 5, and the range is y is greater than or equal to -1. It occurs to me that I believe we were asked to put the domain and range in the warm-up, weren't we? On the previous page. And just to make sure, I mean, I think you get this, but to put it on here, the domain of this is x is greater than or equal to 0. The range is y is greater than or equal to 0. And I think that's important because I'd like to talk briefly about the domain and range of this example 1a. I want you to note that this is h and this is k. But I have a question for you. Why did the domain go from, for the original function, the domain of this little guy is x is greater than or equal to 0. X is greater than something for the original. Why did the domain flip to become x is less than or equal to for the new function? Well, it was because b is negative. There's a horizontal reflection. But your domain of these functions will always be x is greater than or equal to h, or x is less than or equal to h. Similarly, your range is always going to be y is greater than or equal to k, or y is less than or equal to k. Who's willing to volunteer an answer to this question? What would be different in this question if the range was y is less than or equal to -1? What would have had to be different? Madison? Right, which would mean there would be a vertical reflection, and that would mean that a is negative. And that would change the whole picture. But okay, let's try another one. There's the function y equals -2 root 2x plus 12 and then plus 3. Take a minute, please, everybody, and give some thought to the value of a, the value of b, the value of h, and the value of k. Not at every opportunity, but at many opportunities, I'm going to hit you with that thing again where you have to factor b out to find h so you don't get caught on an exam. This written in standard kind of template form would be y equals -2 times the square root of 2 multiplied by, in brackets, x plus 6 and then plus 3. So I have to factor that 2 out. Well, I mean, how many of you looked at that and understood that h was -6, but you didn't have to physically on paper factor the 2 out? Some of you might kind of look ahead in your head and do that, and that's great. But just to really reveal it, I'm going to do the following. Factor the 2 out and be left with x plus 6. What does that give me for a? A is the coefficient in front of the function. B is the coefficient in the argument in front of the x's, which is 2. K is the number that's added to the function after everything else happens, and that's 3. And then h, of course, since we have x minus -h, or x minus -6, gives you x plus 6. h is negative 6. And you know everything I just said there about the h. You know h is the opposite of the number, right? If it's x plus 6, h is negative 6. So we are going to reflect things vertically. We'll have a vertical reflection. We will have a vertical stretch by a factor of 2. We will have a horizontal stretch by a factor of a half. We will shift it 6 units to the left and 3 units down. My prediction, everybody, is that the vertex of this is going to be at negative 6 comma 3. My prediction is that the domain will be x is greater than or equal to negative 6, because that's h. And my prediction for the range is that y is going to be related to k, which is 3, but I'm going to put less than or equal to because there was a vertical reflection, which means the thing will go downward instead of upward. Go ahead, Shazmaida. Pardon me? Thank you very much. It is not 3 units down. It is, without a doubt, 3 units up. Thank you. Okay. So, you know, if we do this systematically, there are other ways to do it, but if we take point by point and apply all of these, reflect that point that I've highlighted vertically, stretch it vertically by a factor of 2, stretch it horizontally by a factor of a half, doesn't move. So it's going to now be shifted 6 to the left and 3 up, which is going to put it here. Well, that'll be where the vertex is, negative 6 comma 3. Moving on, I take this point and I reflect it vertically, which means it's now going to be 1 below the x-axis. I stretch it vertically by a factor of 2, which means it's going to be twice as far away from the x-axis. I stretch it horizontally by a factor of a half, which means it's going to be here. And then I have to move that point 6 to the left and 3 up. I'm just going to put an arrow here to mark where this point is and then talk about that location in a second. 1, 2, 3, 4, 5, 6. 1, 2, 3. This was here, correct? You didn't need to shift it and count squares. What you could have done is said, in relation to the vertex, this point is half over and 2 down. And if you take a look at what we've got over there, if I go from our new vertex a half over and 2 down, I have it. So you can always replot these points by talking about where they are relative to some other point that we already know the location of. Let's do one more. I reflect vertically, and then I stretch vertically by a factor of 2. I hope it's clear, although I don't know that I've ever told you this. I could have stretched it and then reflected it, and it ends up in the same place. I stretch that horizontally by a factor of a half. It's going to be half as close. And now I shift it 6 to the right and 6 to the left and 3 up. If you look at where that point is relative to the vertex, from the vertex, if we go over 2 and down 4, that's where the point is. Okay. But we're shifting at 1, 2, 3, 4, 5, 6 to the left and 1, 2, 3 up. You will notice that it is 2 to the right and 4 down from the vertex. So what this graph will look like is something like that. Is the domain x is greater than or equal to negative 6? Yes. Is the range y is less than or equal to 3? Yes. And what I am getting at is I think you should be able to come up with the domain and range in the vertex without actually graphing it. And this becomes important because on an exam, I could give you the following situation. And just to jazz things up a bit, I've changed H to P. I could use any letters I want. If I tell you now that A is negative and B is positive, you should be able to tell me what the domain and range are, even though you don't have any numbers. The domain would be X is greater than or equal to P, and the range would be Y is less than or equal to K. Because A is positive, the graph is going to move up. It's going to start at wherever the vertex is and go up. But the vertex will be at P comma K. So if the vertex has a y coordinate of k and the graph moves up, y is greater than or equal to k. You have to be able to think more abstractly rather than looking at a graph. Similarly, there's this point, P comma K. I could care less where it is. And this graph is going to move up, but it's also going to move to the left. Why is it going to move to the left? Because B is negative, so there's a horizontal reflection. Which would mean that, did I just second here? Oh, no. I got this wrong. It's moving down because there's a vertical reflection, and it's moving to the right because B is positive. Sorry, I thought for a second B was negative. So this is saying it still goes to the right. This is saying it goes down. Does that make sense? Okay. All right, let's move on to the next example. Determine the equation of the radical function. So this time, we're given the graph and asked to find the equation. Well, what you should put on here are some key points on the original function. The original function is the square root of x. It has to start at the origin and go through 1, 1 and 4, 2. I don't know necessarily that you need to add this to the graph, but we're going to be looking at those key points to find out what happens to them to get the new graph so that we can determine A, B, H, and K. So this is where, quite frankly, that shortcut becomes very useful. I don't care that A and B happen first. A and B will not move the vertex, which means the new vertex is determined solely by H and K. Since the new vertex is at 7, 5, after A and B are applied, we must shift the graph 7 to the right and 5 up. Doesn't matter what A and B are. They're not going to move the vertex. The only things that will move the vertex are H and K. Now, there are a couple of ways for you to figure out the value of A and B. Okay. When we have a key point, I want you to notice that the vertical distance between the vertex and the first key point is 1. The vertical distance between those two key points is 1. And when I look at the vertical distance between these two key points, the vertical distance is 4. And that means there has to be a vertical stretch by a factor of 4 somewhere in relation to those two key points. Which means A has to contain the number 4, but visually we can see that the graph is moving down and not up, which means there's also a vertical reflection. When we look at B, what I'm going to do now is look at the horizontal distance between the two original key points, and the horizontal distance is 1. When I look at the horizontal distance between the two key points afterwards, the horizontal distance is 3. Yes? That means there's a horizontal stretch by a factor of 3, which means that B has to contain a third. Did you see what I almost did there? I almost put a horizontal stretch by a factor of a third. When I told you you're going to stumble on the B stretch factor thing, we all stumble. Okay. I also can see visually that the original graph, which I have knowledge of, moves to the right, which means the new graph, which moves to the left, has to be arrived at by using a horizontal reflection. So now we are going to apply all of that to y equals a f of, well, f is the square root, b times x minus h plus k. And if you were to graph that on your graphing calculator, you would discover that it has a vertex at 7, 5, and it will go through that point 4, 1. Good? We're not done. Now, I don't want you to write anything else necessarily, but I want to show you, and this is going to happen in this course and on exams and on the diploma exam if you write it, sometimes you can arrive at the destination by taking different routes. We can get this function by using a different set of transformations. For example, I could say, you know what? This is 7, this is 5, yes? Let's just say b is negative 1. Let's see what happens. B is negative 1. If b is negative 1, and it has to be negative because it moves to the left, this is our function. Yes? What I have is a missing parameter. I don't know a. And you've been taught again and again and again by me that if you have a missing parameter, go ahead and put in an ordered pair for x and y and see what the missing parameter has to have a value of. So I'm going to put in 1 for y. I'm going to put in negative 1 times x is 4 minus 7. Plus 5. Sorry, I had to think ahead about something. So let's solve this for a. Let's see what we get. 1 equals a root 3. 4 minus 7 is negative 3 times negative 1 is 3. Plus 5. I subtract 5 from both sides. And I get a equals negative 4 over root 3. You with me? What does that mean the function is? Y equals negative 4 over root 3 root negative 1 x minus 7 plus 5. What we had before was y equals negative 4 root negative 1/3 x minus 7 plus 5. How many of you see those are the same things? That square root of 3, instead of saying times the square root of 3, I could just put it underneath the square root. Or another way to look at it, I could move this root 3 out and put root 3 on the bottom and have the negative 1 x minus 7 plus 5. They're the same thing. They appear different, but they're the same. If you wanted to, you could have done the whole thing by saying a is negative 1 and calculating the b value. And if you did that, you would end up with y equals -1, you would have -16 thirds here. Because the square root of 16 is 4, so you could do that and move it out in front. And I'm only pointing this out to you not because it's necessarily going to happen, but you might see an answer on an exam that looks different than your answer because it was arrived at in a different way, but it's the same result. This is by far the trickiest thing of this lesson, is understanding this. So I wouldn't get bogged down in it. We have, I believe, one more question to do. No, two. One more. Yeah, example 3. A, B, H, and K. Reagan. If a function is reflected horizontally in the y-axis, if something is reflected horizontally in the y-axis, which of those 4 parameters is affected? B. And what does that do to B? It's negative. Okay, so we're just going bit by bit here. If we stretch something horizontally by a factor of 3, which of the 4 parameters changes? Correct. And what will B be? 1/3. So all we're doing is we're translating this word salad into math. That's what we're doing. Stretched vertically by a factor of 1/2. If it's stretched vertically by a factor of 1/2, Jonathan, which of the 4 parameters is affected when we have a vertical stretch?
A.
And what will A become?
A will become 1/2. Oh.
Say again? I just didn't hear you, that's all.
A will become 1/2.
A will become 1/2. I kind of looked at you funny because I just didn't hear you. 1/2 is correct. If we shift it 5 units up and 4 units to the left, I think that's pretty clear that since it shifts to the left, h is negative and it's -4, and shifts up, k is positive and k is 5. We're okay with h and k, I hope. So we put it together. Y equals a f of, but f of is the square root. This goes back way back to the second lesson or something, or the first lesson where we talked about that function notation. If f of x was sine x, then I would write sine and put a set of brackets. B, bracket x minus h. Well, if I subtract -4, that's the same as adding 4, plus k, and we're done. We've kind of snuck in a little bit of algebra here in terms of finding missing parameters, but this lesson is nothing new. And I've actually in the past thought of just not teaching this lesson, because really all it's about is transforming a graph. But I worry that you would miss out on something. Bottom line is you need to be able to take y equals root x and apply transformations to it. As usual, we've got some text questions, some multiple choice and numerical response questions. I'll just make a note to you that if you haven't been doing all of the multiple choice numerical response questions, those are really, really crucial. And I only say that because I was a little surprised nobody had any questions from yesterday's. Make sure you do them. Like if you didn't do the ones from yesterday, put that on your bucket list as well of things to do. Get that done and out of the way. Because it's not really a bucket list. Things to do. Okay? Give me a second to clip my recording and get it up to my channel, and then I will be around to help you out.